Welcome back to Mech 1330. We're getting into Chapter 10 in your book now, Basic Principles of Pneumatics. All right, so we're leaving hydraulics behind now, and the next chapters that we're going to talk about are all going to be on pneumatics and understanding what they are and how they work. All right, so the whole point of pneumatics now is we're going to use gas to transmit power from one point to another, where with hydraulics, we were transmitting oil, or to transmit power from one end to another, or using oil, okay? Nothing changes. Force equals pressure times area, or pressure equals force over area, or area equals force over pressure. Equation still hasn't changed from Chapter 2, all right? But if we sit back and we take a comparison at hydraulics and pneumatics, okay? So hydraulic, relatively incompressible liquid, right? We're using oil. Hydraulics were slow, smooth motion. They were very precise. They were self-lubricating. They definitely are not as clean. I think you guys found out about that a lot in the lab. All right, and the pressures that we work with are 500 to 5,000 psi. We can go way above 5,000 psi, but those are, the general, form of what we're using for there, or the general pressures that we stay between. Okay, pneumatics now. We use a compressible gas, right? We compress air into a tank. We can store it, use it that way. Okay, they're very quick and jumpy. They're not as precise as hydraulics, and we have to add lubrication to the line. Now, a lot of you guys, we've used the pneumatic nailer in class already, right? A couple drops of oil in the line before we connect the hose onto it. Pneumatics, definitely the cleanest. We use those, right, in more of a clean facility. And general pressures around pneumatics are around 100 psi when we're using them. Okay, now we need to start talking about different types of pressures that we're going to use for the next few chapters. Okay, we have gauge pressure. Pressure that is above atmospheric pressure. Okay, everything we base stuff on is going to be at atmospheric pressure, and then we're going to go above it. Okay, for anything that we're doing or using equipment, or we're going to go below it if we want to create a vacuum. Okay, so we're going to talk about that at the end of the chapter. Okay. But atmospheric pressure, what that is, that's the weight of the air above us as we stand. The entire atmosphere is sitting on us. Kind of like if you go and you start diving in the ocean, you have the weight of the ocean on top of you as well. So atmospheric pressure or gauge pressure or things like that, okay, it is going to vary, whether we're at sea level or up at the top of a mountain or things like that, because atmospheric pressure is going to change, okay? Now that we know that, all right, absolute pressure, that's the total pressure exerted on a system. So the pressure that's in the system plus the atmospheric pressure that is above it. Okay, so we have the absolute pressure is the gauge pressure, okay, plus the normal pressure above us, okay? So that's absolute. Atmosphere plus gauge, okay? Now, absolute pressure, when we start talking about it in imperial units, it's PSI-A, pounds per square inch atmosphere, or kPa absolute. Okay? Our gauge pressure is PSI, pounds per square inch. That hasn't changed. We just throw a G at the end, and it's the gauge. All right, so P sig. And then kPa gauge. And then atmospheric pressure, we're going to use PSI-A, or kPa absolute. Okay? So if we're talking atmospheric pressure, okay, I think I said absolute, it should be atmospheric. Okay, now what we use are the following two pieces. For atmospheric pressure, when we're doing our imperial calculations, we will use 14.7 psi. Okay, when we are at sea level, we're going to use 101 kPa for metric. Okay, so that 14.7 and that 101 are very important. We're going to use them throughout the next few chapters through all of our calculations. Okay, now we touched on this briefly, I think like way back in chapter 1 when we start talking about temperatures, okay? So absolute zero is minus 460 Fahrenheit, which is the same thing as negative 273 Celsius, which is 0 Rankine, okay? So Rankine is our imperialistic absolute scale. Okay, so we have Rankine and Fahrenheit when we're talking imperial units and temperature-wise, okay? So that's our absolute. In metric, we use Celsius and we use Kelvin. Kelvin's the absolute, Okay, so to get Rankine, you're going to take Fahrenheit plus 460. Okay, to get Kelvin, you're going to take Celsius plus 273. So in our standard imperial units, we have to do everything in Rankine, which is absolute temperature. In our metric units, we're going to do everything in Kelvin, which is our absolute temperature. All right, so we're going to get into the gas laws now. The first one we want to look at is called an isothermal process. Okay, it's a process in which temperature remains the same. So the word even kind of tells us there. Iso, all right, it's concentrated, nothing's changing. Thermal, we're talking temperature, heat, those sort of things. So the first one we want to look at is Boyle's law. Boyle's law. The absolute pressure of a confined gas is inversely proportional to its volume as long as temperature remains constant. So Boyle's law applies to an isothermal process. Okay, we're going to learn about 3 different laws, and then we're going to put them together and call them the gas law. Okay, so Boyle's law, since temperature is constant, it's not part of the equation. So it's really just going to be P1V1 equals P2V2. So pressure times volume equals pressure times volume. Okay? Here's the key thing at the bottom of the notes here. You always have to use absolute pressure. We're going to talk through that when we go through an example here. We have a cylinder. It's initially filled with 4 cubic feet of air at a pressure of 20 psig. All right? The air is compressed to a volume of 1 cubic foot. What's the pressure in psig after compression? Okay? So, a couple different things we have to do here. First step, we have to get to absolute pressure. And since we are using imperial units, okay, we have to add 14.7. Okay, so we're going to take our gauge pressure, which is 20, right? That's our psig, pounds per square inch gauge. That's our 20, plus we add our atmospheric pressure of 14.7. So we have to use 34.7 psi for our absolute pressure. Okay? Now we can calculate our new pressure using the given pressures in the system, right? We're using Boyle's law. Okay? P2 is equal to P1 times V1 divided by V2. We're using the equation on the previous slide, and we're solving it for P2. All right? So we're using our pressure, that's absolute pressure, 34.7 psi, times 4 cubic feet divided by 1 cubic foot, feet cubed cancel, okay? And we're left with 138.8 psi absolute. Now, we have to go back and take out atmospheric because we want a gauge reading. Okay, so we're going to take that 138.8, subtract back out the 14.7 atmospheric pressure, and we're left with 124.1 psig. Okay, so that's a gas law using Boyle's law when temperature is remaining constant. Okay, let's do the same problem here, only we're going to do it with metric units instead of imperial units. Okay, we have a cylinder initially filled with 2 cubic meters of air at a pressure of 140 kPa. Remember, please notice that there's a K in front of that PA, so there's 3 more zeros that go after that 140. The air is compressed to a volume of 0.5 cubic meters. What is the pressure P2 in kPa after compression? Okay, so we're going to follow suit here with the same thing. We have to convert our kPa to absolute pressure. So we have to add atmospheric pressure. So remember, anytime we're using metric atmospheric pressure, we're going to use 101 kPa. So we've got to take 140 kPa gauge plus 101 kPa atmospheric. Okay, that's going to give us 241 kPa absolute. Okay, we have to calculate our new pressure now using Boyle's law. So P2 is P1 times V1 divided by V2. Substituting our numbers, we get 964 kPa absolute. All right, so we've got to take that absolute, all right, and subtract back out the 101. So we're going to take 964 minus 101 and get 863 kPa for our new pressure. Do have a slight typo in that first convert to kPa absolute. Next to the 101 kPa, that should be atmospheric, not ABS. It should be atmosphere ATM. Okay, so next to that first 101. Okay, so please, I don't want to confuse you there, but I just noticed that as we're taking a look at it. Okay. All right. The next we're going to do is Gay-Lussac's law. That's the absolute pressure of a confined gas is proportional to its temperature provided its volume remains constant. Okay, so we're going to use this law anytime volume is constant. So we have a pressure and we have a temperature. Okay, and then after it goes through some sort of, experiment or what we're doing with it. Okay, so let's do an example here. We have air in a fixed volume container is initially at atmospheric pressure of 0. Okay, so we're reading the gauge there. And 80 Fahrenheit. Its temperature is then raised to 160 Fahrenheit. What is the gauge pressure at the final temperature? Okay, so we have to get into absolute temperature first. Okay, so we have to take 80 plus 460 because we have to be in Rankine, and right? So it's going to be our Fahrenheit plus 460 to get into Rankine. So our first temperature is 80 plus 460, so that's our initial temperature. And we get 540 Rankine. And then our second temperature, what we end at, is 160 Fahrenheit plus 460. That gets us to 620 Rankine. So it's imperative that you put all of these in absolute temperature first. Now, we have to get into absolute pressure, and since this is imperial, we're going to take our gauge pressure, which is 0, plus our atmospheric pressure, which is 14.7. So our initial pressure here is 14.7. Okay, and now we use Gay-Lussac's law, all right, to solve for this. So P2 is going to equal P1 times T2 divided by T1. All right, all we did was take Gay-Lussac's law and solve it for P2. Now we're substituting in the values that we have, so our first pressure is 14.7, and then we're going to multiply by the ratio of 620 divided by 540, and we get 16.88 atmospheric pressure. So just like everything else, the last step, we have to remove out atmosphere to get back to gauge. Okay, so we're going to take 16.88 minus 14.7, okay, atmospheres. So that gives us 2.2 gauge pressure, PSI gauge. All right, next, okay, we're going to do one that's metric. Same concept. Air in a fixed volume container is initially at an atmospheric pressure of 0 kPa gauge and 30 degrees Celsius. Its temperature is then raised to 90 degrees Celsius. What's the gauge pressure at the final temperature? All right, so the equation is going to be the same. We've just got to make sure that we get into the right temperatures now and the right pressures in metric. Okay, so we've got to get to absolute temperature. So we know in order to get to Kelvin, we're going to have to take our Celsius plus 273. Okay, so we're going to take 30 plus 273, which is our initial temperature, and then we're going to have 90 plus 273, which is our final temperature. Okay, so we're going to have 303 Kelvin and 363 Kelvin. To do this, we have to convert to absolute pressure. Okay, so we're going to take our gauge pressure plus our atmospheric pressure of 101 kPa, add those together, and we get 101 absolute pressure. Now we can do our calculation. The final pressure, P2, is going to equal P1 times T2 over T1. So it's 101 times 363 over 303. And we get 121 kPa absolute pressure. Remember, that's not the pressure we're looking for. We're looking for gauge pressure. So we're going to have to take that 101 kPa that's absolute, subtract out atmospheric pressure, 101 kPa, to get our answer. So when we do that, we end up getting 20 kPa on our gauge. All right, the third gas law is Charles' law. So the volume in a confined gas is proportional to its temperature, provided its pressure remains constant. So in this equation, We are not using pressure. Okay, pressure is constant, so it would cancel out on both sides. So now we're relating volume and temperature. Okay, so there's three laws we're talking about. We've got Boyd's law, right? Where temperature is constant. We have the gas law, or the last one we did, Gay-Lussac, where volume was constant. Okay, and then we have Charles' law here, where pressure is constant. Okay, so we're gonna combine those and make the gas law. All right, but let's do an example using Charles' law. We have air held in a container with a free sliding piston. It's initially at a temperature of 80 degrees Fahrenheit and a volume of 0.65 cubic feet. Its temperature is then raised to 260 Fahrenheit. What's the volume of the air after being heated? Okay, so first things first, convert our temperatures to absolute. So we've got to take 80 plus 460 to get 540 Rankine, and we got to take 260 plus 460 to get 720 Rankine. Okay, so we are now in absolute temperatures. All right, there's nothing we have to do to get into absolute volume. So since pressure is not part of this, we don't have to mess with any of that. We can use Charles' law here and solve for volume 2. So V2 is equal to V1 times T2 over T1. So we're going to get 0.65 times 720 divided by 540, and we get 0.867 cubic feet. That will be our final volume. Okay. Now, if we take a look at the general gas law itself, we are combining Boyle's law, Gay-Lussac's law, and Charles' law. And then, essentially this is what it is. Nothing's constant now. Okay, so we're putting all three of those laws together, and now nothing's constant. So we're going to get P1V1 divided by T1 is equal to P2V2 divided by T2. You should be able to solve algebraically for any one of those variables. So let's do an example here using the general gas law. Nothing's constant, right? Air initially at 15 degrees Celsius and 800 kPa occupies a volume of 3 cubic meters. If the air is heated to 170 degrees Celsius, while its volume is reduced to 0.3 cubic meters, what's the resulting final pressure? Okay, so we're going to use the gas law and solve for P2. Okay, our initial stuff is always going to be the 1, and our final stuff is always going to be the 2. So first things first, we have to get absolute temperature. We should know how to do this one by now. All right, we are in Celsius. We got to go to Kelvin. Okay, so we're going to take 15 plus 273, and we're going to take 170 plus 273. So we're going to be using 288 Kelvin and 443 Kelvin. Okay, and then we have our initial pressure of 800. So we've got to use that. That's our gauge pressure. And then we have our atmospheric pressure, which is 101. So when we add those together, we get 901 kPa, and that's our absolute pressure. Once we have all those conversions done, we're ready to calculate our final pressure and just substituting into the equation. So we're going to get T2 times P1 times V1, all divided by T1 times V2. Now, if you're using your calculator, put all of the numerator and all of the denominator in parentheses before you do this calculation. All right? So when you get that final pressure, we're going to get 13,851 kPa, and that's going to be absolute. We have to make sure that we want gauge pressure. Okay, so we are going to subtract out 101 kPa from that answer to get us the gauge pressure. So hopefully we're used to the fact that we should be doing that now. Convert all the temperatures and convert everything to atmosphere, and then back out of atmosphere. Or not absolute. Convert to absolute, back out of absolute. Okay, so last one here, adiabatic process, where we have none of the heat transferred to the atmosphere, so the temperature of the gas is going to increase at a maximum when compressed or expanded. Okay, so the temperature is changing without heat being added. We have a constant here, so we're going to use the constant for different elements. If I give you a different element, I'll give you the constant for it. But for air, it's 1.4. And we're going to be substituting into the given equations here. All right, if we solve our problem in an adiabatic process. Okay, and the problem in general on your homework or test will say adiabatic, so you'll be able to recognize that and plug in accordingly. All right, so let's do an adiabatic process here. Air that is initially at 80 degrees Fahrenheit and atmospheric pressure is compressed from 10 cubic feet to 2 cubic feet. Assuming the process is adiabatic, okay, what is the final pressure and temperature of the gas? Okay, so first things first, convert to absolute temperature. So you got to take 80 plus 460. Okay, for that one, we're going to calculate our new pressure using the adiabatic process. So you have to use the constant of 1.4. So we're going to take 14.7 times 10 cubic feet to the 1.4 power divided by 2 cubic feet to the 1.4 power. Now, make sure that you use enough parentheses in your calculator to overcome the order of operation issues that could happen here. All right, when we did that, we should get 139.92 psia absolute, okay? And we have to convert it back to gauge, so we're going to subtract 101 kPa because we're in metric out of that. All right, or sorry, we are not in metric. We're going to subtract out 14.7 psia atmosphere. All right, so we end up with 125.22 gauge pressure for this problem. Okay. Now, the final temperature, okay, we have to solve the equation for T2. Okay, on the previous slide, substitute all your given values. All right, you're using Rankine. All right, you have to go back to Fahrenheit. So once you get the temperature in Rankine, you're going to subtract out 460 and end up in Fahrenheit. All right, let's talk about some basic units. When we talk about gas flow, we want to use SCFM, standard cubic feet per minute. It's going to be a common term that we're going to use back and forth. If we're talking something in metric, it's going to be cubic meters per minute. All right, our standard ideal conditions, right, are at 68 Fahrenheit, 14.7 atmospheric pressure, and relative humidity being about 36%. All right, so that's the equivalent flow of atmospheric air, not necessarily pressurized air. Well, why is that all important? Because we're going to talk about vacuums now. All right, so with a vacuum, right, we use vacuums to pick things up. So what creates a vacuum is when we drop below atmospheric pressure. When we drop below atmospheric pressure, we use that to create suction. And that's how we pick things up. So like station 1 on our 870 trainer, right, we got our pick in place, comes down, turns on the vacuum, all right, picks up our valve body and moves it to the next station. So how do we measure things in a vacuum? Okay, it's measured in mercury. So you're going to see Hg through a lot of this. Okay, and we use mercury in a barometer. So if we do everything in metric, it's going to be millimeters of mercury, or you're going to see mmHg. So if you recognize Hg from the periodic table, it's mercury. Why do we use mercury? Because it's a heavy liquid. Okay, and at sea level, the air pressure will push mercury to a height of 30 inches. So 30 inches of mercury represents what we call a perfect vacuum. So at higher elevations, it's going to be less than 30 because the atmospheric pressure is not as high, right? We're up on a mountain, all right? There's not as much atmosphere over it. A vacuum generates less force at higher elevations, all right, because we aren't going under as much atmospheric pressure. How do we create vacuums? All right, we can generate vacuums using vacuum pumps. They're not perfect. They cannot evacuate all the air, but they're very efficient. All right, industry pumps operate in about 20 inches of mercury. Atmospheric pressure for this, all right, is 0 on the gauge, 14.7 atmospheric. So for us, that equals 0 inches of mercury when we are at sea level. Okay, now 1 inch of mercury is negative 0.49 gauge at sea level, and then 1 millimeter of mercury is negative 0.13 kPa gauge at sea level. So you need to know those two numbers, whether we're in imperial units or metric units, of what's happening if we have an inch of mercury or if we have a millimeter of mercury. Okay? So anytime we remove air, we're decreasing pressure. So let's do an example here of a calculation using a vacuum. We have a suction cup that has an inside diameter of 3 inches. We use it in a vacuum system that pulls 20 inches of mercury. What is the maximum lifting force? Okay, so we have to convert to gauge first. So 20 inches of mercury times negative 0.491 gauge divided by 1 inch of mercury. All right, all that I was given to you on the last slide. Okay, so our gauge is negative 9.82. as usual, we calculate the area, pi d squared over 4. Okay, and then force, right, hasn't changed since chapter 2, is pressure times area. So now we're going to take negative 9.82 pounds per square inch times 7.06. We're going to get negative 69.422. Okay, well, the negative should be significant for us. That should tell you something that we are picking things up. Okay, so the negative indicates that the object is being drawn towards the suction cup. Okay, so there's how we can calculate a vacuum. So let's do the same calculation here, doing something in metric. Okay, we have a suction cup with an inside diameter of 40 millimeters, is to be used in a vacuum system that pulls 200 millimeters of mercury. What's the maximum lifting force? Force is still pressure times area. It's really just for us to do our conversions here. All right, so we got to convert our mercury to gauge. Okay, so we have 20 millimeters of mercury times negative 0.13 kPa gauge divided by 1 millimeter of mercury, right? That's from a couple slides back where I gave you that number. All right, so we're going to get negative 26.6 kPa gauge. Then we have to calculate the area. Since it's 40 millimeters, we have to move the decimal 3 places to the left before we calculate area. T is 0.04 meters. All right, so make sure you're doing that. Then force, right, is pressure times area. And we get negative 33.5 newtons, all right? Negative, once again, indicating we're lifting something up. So the basics, guys, for us of a pneumatic system here is, one, the power supply. Okay, so that's our compressor or our receiver tank. And we're going to talk about those in a future chapter here soon. All right, so our power supply is the compressed air sitting in our tank. Our prime mover is still usually an electric motor. All right, and our compressor pumps air into the receiver tank, and we store the air, and then the system draws from the tank as needed, just like we have in class, right? The outside wall, we got a big tank that sits out there. As we need it, it pulls from that tank. We also still have control valves, so directional, pressure, and flow. And then there's still an output, right? General, it's a cylinder, right? We want linear movements or, vertical movements. And then we do have motors, right? There's a lot of cool tools that you guys have that are pneumatic drills or those sort of things. So, all right, guys. Well, that is an introduction to the basics of pneumatics, okay? And the gas laws, all right? We had Boyle's law, Gay-Lussac's law, and Charles' law, and we've used all those different laws, all right, that were either isolating temperature, pressure, and volume. We convert them into the gas law, all right, so we were able to use that depending on the system. We talked a little bit about adiabatic systems, all right, and then lastly we talked about, how we calculate using a vacuum system to pick things up, all right. Well, that is it. We will now be starting our pneumatic labs in class as well, so I think those will be a lot of fun for you guys. Anyhow, got any questions, feel free to email me or ask me before class if you need to. Else, have a great day. I'll see you in lab.